Right, this is 3.2.1, interference. So we're going to start off with some rules for the path difference for when you have two waves that are identical, for them to interfere either constructively or destructively. They'll have different path differences. So for constructive interference, the waves must be in phase. And if they are in phase, then their path difference will be some integer value of their wavelength. So for constructive interference, the waves are in phase. And the path difference is equal to n lambda, where n is an integer. So n can be equal to 0, 1, 2, 3, etc. For destructive interference, we need it so that a crest meets a trough. And in order for a crest to meet a trough, we need to have an n times number of wavelengths plus another half wavelength. Because if you were to shift a wave by half a wavelength, then the crest will meet a trough. Yeah? So the path difference for destructive interference is equal to n plus a half lambda. And again, n is still an integer value. So 0, 1, 2, 3, etc. So when n is 0, the path difference for destructive interference becomes a half lambda. If n is 1, then the path difference becomes 3 over 2 lambda. If n is 2, then the path difference becomes 5 over 2 lambda. And when you have destructive interference, the waves are no longer in phase, but they're now out of phase by pi radians. So next we'll talk about diffraction. So first I want to construct a straight line which represents some axis. Next I want to create a slit where diffraction will occur. So this is our slit. And we want a wave front to pass through here. So we'll draw some wave fronts coming in. Now, when the wave passes through the slit then behaves as an emitter, and the wave will then spread out. So our wave begins to look like this. And you get a single slit diffraction pattern. So you end up with a central bright maxima with a few fringes on the side, which decay very quickly. So the brightest spot is in the center, and then you get smaller bright spots that come in and out next to it. So we'll just represent those with some arrowheads. So there's our first bright spot. Then we'll have another one. And another one. So diffraction occurs when waves pass through a slit. A maximum diffraction occurs when the slit width is roughly equal to the wavelength of the wave. But de Broglie wavelength is about matter waves, so matter behaving as waves. Here we're just purely speaking about waves. But yeah, it's the same principle. The arrowheads just represent the location of the maxima. So you have one bright spot directly in the center, then it gets a little bit darker, then you get another little bright spot, not as bright as the first one, the central is the brightest.
But it still alternates between bright and dark, but even the brightest get darker gradually.
Yeah. So very quickly, with single slit diffraction, very, very quickly, the bright spots will fade into nothingness. So it's unlike interference, where interference you'll have many bright spots, and the bright spots will pretty much be the same or very close brightness to the central fringe. But in case of single slit diffraction, they decay off very quickly. Well, we only draw 3 because the next order are very small, very quickly. Even those ones are very small compared to the central. We can draw more. It's the airy disk. So if you remember, we did the airy pattern of the airy disk in the previous module. It's the same thing. So next, let's talk about Young's double slit experiment. Now this experiment was carried out in multiple different ways. It was used to look at interference between electrons, an electron beam. In this situation, we're just purely talking about waves and what happens with waves. So for Young's double slit, what we have is we have a laser, or any source of light really, but to keep it simple, we use a laser. We use a laser because lasers are monochromatic, which means that they've only got a single wavelength, single color, and they usually emit coherent light. And coherent just means that all the waves have a constant phase relationship. So the phase difference between each part of the wave or each emitted wave does not change. Because if it did change, then we run into other more complex issues. Because any interference that happens, we don't want it because the waves that were emitted were different from each other. We want the waves to be identical, right? With other sources of light, for example, a light bulb or the sun, we will not be a coherent light source because it emits many types of waves, and some of the waves will have a different phase relationship. There'll be different frequencies, etc. So a single wavelength, single frequency, and we want the phase relationship between each wave to be the same. We don't want the relationships to be changing. So we start with a laser. So we emit some wave fronts. We first pass through a single slit that causes diffraction to occur. And then we can pass through a double slit. And so the double slit then has two sources, or behaves like two sources of light. So diffraction occurs at one, and diffraction occurs at the other. And then you can see at some points, the crests of each wave overlap. And at some points, a crest and a trough overlap. And you end up getting an interference pattern. So you'll get one fringe, two fringes. It'll look something like this. So the phenomena here that happens are: one, diffraction at the slits, and two is interference, where waves superpose. And then underneath laser, I'm going to write down monochromatic. Okay, start a new page. Now the laser produces monochromatic and coherent light. So we'll start with monochromatic, which comes from two words. Mono, which means one or single, and chroma, which means color. So monochromatic means one color, and the color of a wave or of light is determined by its wavelength and frequency. So it's one color, single wavelength, and by extension, frequency. And the next is coherent, which just means there's a constant phase relationship. Between all parts of the laser light. So next we'll look at the appearance of the fringes. With a laser and with white light. So with a laser we get a central bright fringe, and then we get some more bright fringes on the sides. So this is our central fringe. Now with white light, I'm going to draw this a little bit differently. So first I'm going to draw two dotted lines. It will help me to draw this easier. And then what I will do is I'll do a few more dotted lines. So allow me to draw this first, and then it will make more sense once I've drawn it. Okay, so what I've tried to draw here is if you've got white light, you know that white light is made of all the other colors of light. Yeah? When white light goes through the double slit, diffraction occurs at both slits and then interference happens. Now for every single color, the central fringe is located in the exact same position, which is in the center. So if every single color lands exactly in the center, you get a central bright white fringe in the center. So this is the central fringe, which is white. Then you've got a dark spot, and after the dark spot, you get spectral fringes. So basically rainbows. Now, because I'm drawing by hand, I'm not going to draw a full rainbow. So I've simplified it down by getting rid of all the colors except for red, green, and blue. Right? If you think of the spectrum, you can think of it as a blue side, which are your violets, your ultraviolets, and then your blue part of the visible light. You can think of the central part of the visible light, which is your greenish parts, and then the other side, which is red, and then your infrared. So I've drawn it in that way. Now what I've also tried to do, and I haven't done the best job at it, is I tried to get all the red fringes to align with the fringes from the red laser. So when they diffract different colors, just like how they refract by different amounts, they also diffract by different amounts. So each of the fringes for each color end up in a different location, depending on the wavelength. So you get central bright fringe, then you get dark, and then you get spectrum. Right, next, let's do an example for two-source interference. Right, next what I want to do is I want to draw a source where diffraction occurs. So I'm going to draw, let's do this. If we add a, we draw it like this. So, I'm try and draw it like this, hopefully it works. So I'm going to draw with two different colors. I'm going to draw with black and I'm going to draw with green. The blacks represent crests and the greens are going to represent troughs. Try that one again. And I'm drawing this by hand, so it's not going to be perfect. I'm going to try and keep them equidistant apart, like that. And then what I want to do is I want to take all of that and I want to create a copy of it. And then I'll place them like that. So you have two sources of waves. And some interesting things will happen. So, where a black line and another black line meet, or a green line and another green line meet, constructive interference occurs. So we're going to mark those with a black X. So at any point where two black lines or two green lines overlap with each other, I'm going to draw a black X. Then, where a black line meets a green line, destructive interference occurs. And I'm going to mark that with a red dot. So wherever we have black and green overlaying on top of each other, we'll mark that with a red dot. And now what I'm going to do is I'm going to draw lines to connect these crosses and dots together. Now I did it by hand, and because I did it by hand, as I'm drawing it by hand, I'm not doing perfect semicircles. There's a little bit of wobble when I'm doing it. So you can see that my lines, while they kind of look like they line up in a straight line, they're a little bit curved. If you did it with a compass and you did it properly, then you'll get perfectly straight lines. But I didn't do that. But you can still see that these X's in the center, they make a straight line. So your central fringe is just all of those connected. Let's try that again. So that's our central fringe. Then we've got another one that connects those X's together, and another one that connects those X's together. And it should be symmetric, but again, because I did it by hand, we might not get that. So here, the path difference is 0 lambda. Let's change back to black. So here you've got 0 lambda, which is n lambda, so that's constructive. Here you've got 1 lambda, which is constructive. And here you've got 1 lambda, which is constructive. Next, I want to join the red lines, or the red dots I should say rather. So if I did it properly, there would roughly be about halfway between. And here you've got destructive, which is a half lambda, and destructive, which is a half lambda again. And you could do this for more, and you can trace out more of the bright and dark fringes by doing this.